Hello, the Fays are sick today, so I'm not going to be here for today's journal entry. And I feel awful about that, but I think we should still be able to cover our topic, which is going to be terminal velocity. So this is journal entry egg 3, so you can go ahead and write that down. And we already have a definition written on the board for us for terminal velocity. It says terminal velocity is the fastest a falling object can go due to air resistance. So why don't you write that down and then we'll get started. Okay, we have two opposing concepts going on. The first we saw with Galileo. Galileo climbs to the top of the Leaning Tower of Pisa, drops off two different masses of cannonballs, and finds out that they hit the ground at the same time. He then proclaims that all objects, regardless of mass, will accelerate down towards the ground at the same rate, and that rate is 9.8 meters per second squared. As we investigated that a little further in the lab yesterday, it appears that that is not always true. Air resistance affects some objects more than others. So if you could pull air resistance out of the picture, in other words, suck all the air out of this room and try yesterday's lab, all of them would accelerate at 9.8 meters per second and hit the ground at the same time. However, air causes some of them to go like this, while others are allowed to fall straight. So we've got a new concept here to talk about, and it's this concept of terminal velocity. Terminal velocity is the fastest a falling object can go due to air resistance. There's a myth that's out there that's kind of interesting. The myth is that if you take a penny and you drop it off the top of the Empire State Building, it will accelerate and accelerate and go faster and faster and faster, so that by the time it hits the ground, it'll be going so fast that it will, and these are the ones I've heard, it will embed itself in the concrete, or it will kill somebody, it will pass through somebody's head. I've heard all of these things before. Well, that myth right there is based on Galileo's idea that an object will continue to accelerate at 9.8 meters per second. But what happens in reality is when the penny is dropped, it does start to accelerate, but as it goes faster and faster and faster, the air resistance increases and increases and increases. If you imagine yourself dropping out of a plane, at first when you jump, you start going faster, 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 you get the butterfly feeling in your stomach. But as you fall faster and faster and faster, it gets windier and windier and windier. So you have the force of gravity pulling down on your body, which we'll call the G force, not to be confused with the guinea pigs. We have the gravitational force pulling you down, and that might be pulling with many hundreds of newtons worth of force. But as you get going faster and faster and faster, accelerating at that 9.8 meters per second squared, it gets windier and windier and windier. So what happens is you wind up with a force of air resistance. And I'll call it air resistance force. That works out well. And you get to a magic spot where the air resistance force and the gravitational force are balanced. Now be careful. This does not mean that you then float in space forever and never smash into the ground. It just means that you will accelerate and accelerate faster and faster and faster until you hit a point where it's so windy you will stop accelerating and you'll keep going at that constant speed. And for a human body, I've seen a variety of numbers. For a human body, if we say about 150 miles per hour for the terminal velocity of a person, that's not a bad guess or estimate. So basically, your body will go faster and faster and faster until you hit 150 miles per hour. Then your body will stop accelerating. You will continue that speed all the way to the ground. We need some text to write over here. A good thing to say would be, well, if terminal velocity is the fastest a falling object can go due to air resistance, it is also the point where air resistance and gravity balance out. So we got the point where air resistance and gravity balance out, and the object stops accelerating. And that should be everything you need.